There are two types of probabilities that we're going to talk about in 10.7. The first one is called empirical probability. All right. The other one's called theoretical, which we're going to get to later in this lesson. Empirical probability, here's the definition, kind of, right? It applies to situations in which we observe things, frequencies and events. So we are observing things. So we're talking about things that have already happened, or we're looking at data, or something like that. So that's what we're talking about when we say empirical probability. Here is how you compute it. You compute it as a fraction or a decimal, all right? So we say this. We say the probability of an event. E is going to be an event, okay? The probability of an event. So the way that we calculate empirical probability, draw yourself a big old long fraction bar because it's a bunch of words that we have to write down. So what we say is we take the observed number of times E occurs. So what I mean by that is, I mean like this E is the same as that E over there. So we look at the observed number of times that thing happens, and we divide that by the total number of observed occurrences. Okay? This is what we do to compute an empirical probability based on things that we observe. So we take the observed number of times that E occurs, divide by the total number of observed occurrences. Okay. So our book gives us this example of empirical probability, which we're going to discuss and go over right now. All right, this is some information that comes from a book from the what was their source? I like to cite the source that they gave us. I didn't say where the source. Just USA, just women. Okay, so here we go. So they give us some information. They give us the mammography screening on 100,000 U.S. women of ages 40 to 50. So we have this screening that happens for women of the ages 40 to 50. You can have a positive or negative mammograph, and then they take a look at the data of women who have cancer versus women who don't have cancer. So I'm going to give you some data that goes in each of these cells right now. So here is the data. I think it's
Whatever you want.
So for positive mammograms, ages 40 to 50, with cancer, 720 women. Okay, now remember we have 100,000. All right. Negative mammograms with cancer. Do you think that number would be more or less than 720 just compared to what we have? So if you test for a negative mammogram, would you think it'd be more or less than 720?
What's the difference between positive and negative?
Positive mammogram means that they found positive cancer cells. The negative means they didn't find any cancer cells. So less. Okay, good. So there's 80. All right. So they found 80 in this one. So yeah, of the positive mammograms, right, 720 had cancer. So that the mammogram test would indicate more likely to have cancer than not. But of the 100,000, 80 of them had negative, but they still had cancer. Does that make sense? Okay. All right. So yeah, this is a real life example. So some of the terminology we might not be familiar with. Okay. Let's talk about a positive mammogram, but you don't have cancer. The opposite of that, right? So your test came back positive mammogram, but there was no cancer present. There's 6,944 of these women. Okay? Right. Yeah. All right. So the test came back positive, but there was no cancer. Okay? Obviously a lot more than the ones with the positive. Now the other one, okay, negative mammogram and had no cancer. Do you think that number would be higher or lower than the 6,944? What's your instinct say? Higher, right? Higher. And in fact, there's 92,256. Okay, now remember, this is data that's already been collected. We're just observing things about the data. Here's what I want to do with you guys. All right, let's see. If I were to add up every single orange number in that table, what would the sum be?
100,000.
Very good. So we're going to have to do it. Okay, now let's do this. If I was going to add up these two numbers, what did those two numbers there represent for us? Yeah, like 800. How many would this be? So 800 women have cancer, right? Have the cancer. All right. What about this column here? If I add these two numbers up, down, what would these two numbers? What would the sum of that represent?
A large number.
Okay, let's be a little bit more specific than a large number.
9,200.
Yes. Okay. What does that number represent, though? 99,200. Yes. Do not have cancer. All right. Do not. Okay. Now let's go and add up the rows. If I add this way, if I add the 720 and the 6,944, what number does that give me?
7,664.
64. And what does that number represent?
Number of positive.
Yes, the number of positive mammograms. Okay, I'll just put positive mam. And then this one, if I do 80 and I add up this row, what does this number give me? Someone add that up real quick.
92,336.
336. And what does that number represent? Negative mammograms, okay? So I want you to be able to utilize the chart to understand the totals and what it is that we're looking at, all right? We're going to need this information to answer these questions. I have 3 questions that we're going to answer, and I'm going to zoom this down a little bit so that we can see the questions, okay, and everything together. So here's question A. So find the probability that a woman has cancer of this group, okay? We have to know what we're looking at and why we're looking at it. All right, so remember that the definition for the empirical probability is the observed number of times that E occurs. So what would E be in this case? People having cancer, right? And then what would the total number of observed occurrences be?
So it's 800 over 100,000.
He says 800 over 100,000. Who agrees? Is that right? Okay. Someone agrees. Someone says I don't get it. Okay, let's go back to the definition, right? What are we looking for? Probability that a woman has cancer. Okay. So we're looking for the number of times that happens. Which number represents the people who have cancer? The 800 does. Okay. So this is going to be 800 out of, the definition says, the total number of observed occurrences. That would be this number here, huh? There's 100,000 observed occurrences. So that's 800 out of 100,000, which given to us as a decimal point is 0.08. 0.08. Okay? Here's part B and C. Now what we're going to do is we're going to change what it is that we're looking at. So part B says this. Among the women with no cancer, find the probability of a positive mammogram. So among the women with no cancer, find the probability of a positive mammogram. Okay, let me go back up to my chart. So what is my denominator going to be? Okay, among the women with no cancer. So what would 90, isn't it 90?
99,200. No cancer?
What? Yeah, you guys are right. It was this. It's 99,200. Okay? That's our denominator, right? That's our observed. Now, among those, right, find the probability of a positive mammogram. What number is going to tell us that?
6,900.
The 6,944. Why is that the right number to use?
Those are people who don't have cancer.
Because,
Or positive.
that's right, because our observed observations are different now. We're not talking about the total. We're just talking about of the ones who don't have the cancer, which ones came back as a positive mammogram. That was 6,944. So this probability is what? 0.07. Is that what you guys got in your calculators? Can you double check that for me? 0.07?
0.07.
0.07. Part C, among the women with positive mammograms, find the probability of not having the cancer. So among the women with positive mammograms, what number represents the women with positive mammograms?
6.
No. Total positive mammograms, what is it?
800,000.
It's 7,664. Do you guys see that? This is the positive mammograms, right? Right there. 7,664. Okay? So this one is 7,664. Among those women, what's the probability of not having cancer? So of these, which ones don't? That would be this number here. So 6,944. So 6,944. So what would that be as a probability, as a fraction? 0.906 or 0.91. Yeah, exactly. About that. Yep. Okay, here is the next idea. The other type of probability that we're going to talk about is called theoretical probability. That applies to situations in which the sample space only contains equally likely outcomes, all of which are known. Okay, so you don't really have to know that per se, but you have to know the difference between theoretical and empirical. Empirical is based off data. Theoretical is based off a sample space in which we can use to talk about the future or the probability of something happening that hasn't happened yet. Okay, so we have to talk about this word called sample space. Who knows anything about this word called sample space or has heard of this word before? Anybody? Okay, so the sample space then is nothing more than all ways an event can happen. Okay, so all ways that an event can happen. If I'm going to flip a coin, my sample space would consist of a head or tails, right? Because that's all the possible outcomes, right? That's all the ways that something can happen. If I'm going to roll a dice, or die, one die, then my sample space are the numbers 1, 2, 3, 4, 5, and 6. So there are 6 things in my sample space, okay? If I'm going to pick a card, then there are 52 cards in my sample space. Does that make sense? So the sample space is all the ways an event can happen, right? All the ways an event can happen. All right, so the way that we compute it is as following. So the probability of my event happening is another fraction bar. It is the number of outcomes in my event divided by the total number of outcomes in the sample space. I'm going to say SS is sample space. So SS is the same thing as my sample space. Nick, you good, buddy? No? Alright, so let's do an example together of a theoretical probability problem. You're going to roll one die. You're going to roll one die. Alright? And they would like us to compute the probability of getting a number less than 5. Alright? This is a pretty straightforward, simple example, but I really want to harp on the definition that we're going to use to get it. So the definition says the number of outcomes in my sample space, or the number of ways I could get E, divided by the total number in my sample space. So let's construct the sample space for rolling a die. Remember, the sample space is all the ways that something can happen. Okay, so the sample space is going to be a set. It's a collection of different ways that something can happen, right? So if I roll a die, what's one possible outcome that could happen?
1.
I could get the number 1. Do you guys agree with that? Okay, what's another one thing that could happen?
2.
I could get the number 2. I could get 3, 4, 5, or 6. Could I get the number 7? No, because it's a fair die and we don't have the number 7. Could I get the number 1.5? No, because there's only integers on the tops of my dies there, okay? So, my sample space consists of the collection of numbers that could possibly happen. And how many of them are there? There are 6 total outcomes in my sample space. Everybody agree with that part? That's my denominator. That's the denominator, okay? So, if I want the probability of getting a number less than 5, it's going to be something divided by 6 because that's the number of outcomes in the sample space. Now, we want to also compute the number of outcomes in the event. Alright, well the event is a number less than 5. Well, shoot. 1 counts, 2 counts, 3 counts, and 4 counts. But 5 and 6 don't because 5 is not less than 5. So therefore, there are 4 numbers in which the event can happen. There are 6 in the sample space. Therefore, the probability of rolling a number less than 5 is 2/3. Okay, or a fraction, 0.66, whatever you prefer. I'm fine with both. Okay, probability of getting graded for Lily. Did you come up with something?
2/6.
She says 2 divided by 6. Who agrees with Lily? What does the number 2 represent? All the ways that we could get a number greater than 4. What's the number 6 represent? The total in the sample space. Good. So what, a third, right? Okay. So there we go. Okay, I'm going to make you guys guess before we actually compute this, and I want you to tell somebody sitting next to you. You're going to roll 2 fair die, or a pair of dice, whichever you prefer. And I'm interested in calculating the probability that the top 2 numbers are going to add to 8. All right, they're going to add to 8. So now I want you to think about what a good guess might be for that probability. Remember, our probabilities have to be somewhere between 0 and 1. So maybe give me a decimal. And then I'm going to ask you a couple more questions after you think about it for about 2 minutes right now on your own. Ready, set, go. We have some guesses out there, which is really cool. But they're all over the map. So what we're going to do is I'm going to give you guys a way to organize your thoughts here, okay? And I'm going to give you a chart. So the first die could be a 1, a 2, a 3, a 4, a 5, or a 6. Do you guys agree with that? Is that true? Okay, the second die that I roll could also be a 1, a 2, a 3, a 4, a 5, or a 6. This is a very, very handy chart that I'm about to show you. What I'm going to do is I'm going to add up the top 2 numbers. So if I roll a 1 and a 1, then I would have a sum of 2. And notice that there's only one way that I could get that, right? If I roll anything other than a 1 on the first die, then there's no way I can get a 2. Okay? But you'll notice that this is just going to go up by 1 every single time, right? If I roll a 1 and a 6, I'd get 7, a sum of 7, right? Well, this just goes up. So 2, 3, 4, 5, 6, 7, 8, right? 3, 4, 5, 6, 7, 8, 9. 4, 5, 6, 7, 8, 9, 10. 5, 6, 7, 8, 9, 10, 11. And then 6, 7, 8, 9, 10, 11, and 12. So someone tell me, what does this 12 represent? What does that mean?
6 plus 7.
Yeah. There's only one way that I could get a sum of 12. That's if I were to roll a 6 and a 6. That would give me the 12, right? You guys agree with that part? All right. What do you notice? What do you notice about the main diagonal of that right there?
They're all 7.
They're all 7s. You ever?
There's a bunch of different ways to get 7s.
Have you guys ever heard of the term lucky number 7? Okay. This is where it comes from. If you take a look at that, 7, the sum of 7, has the probability of occurring the most often because there's the most combinations to get to 7. For example, I could get a 6 and a 1, a 5 and a 2, a 4 and a 3, a 3 and a 4, a 1 and a 5, or sorry, 2 and a 5, and then a 1 and a 6, right? So that can happen the most. That's why they call it lucky number 7. Okay, so what's our sample space then? 36. Our sample space is 36. Why is our sample space 36?
Because it's like the thing where we do the different meals.
Yeah, right? Look, check it out. I mean, every single one of these is an equally likely event, or can happen equally likely. So I have 36 different options that could happen, right? I could get a sum of 2, a sum of 3. These are all of them. There's 36 accounted for. What we're looking for, though, is what? A sum of what? 8. Okay? So check it out. How many ways can we get a sum of 8? There are a collection of 5 different ways to do it. So the right answer is 5 out of 36. The 2 of you are very correct. So what did you guys come up with? 0.14. There. Okay, you don't have to copy down the question, but I'll read it to you, okay? This is a box number 6. This is an example. It's called the Florida's Lottery Game. In the lotto game in Florida, that should be in Florida, sorry, typo, no big deal. Lottery game in Florida, players choose 6 different numbers from numbers 1 to 53, integers only, right? So if the 6 numbers match 6 numbers drawn randomly, then you win. With 1 lotto ticket purchased, what's the probability of winning? Okay, this is an example of a chart that we could never, ever actually finish writing because there's so many different possibilities. So we have to know something about combinations. Okay, Marty, I see your hand up, buddy. Can you contribute to this conversation?
Yeah, could we, because this problem was in our last homework or similar.
Uh-huh.
So could we use what we learned before?
Absolutely. I love the fact that you use what you learned.
This, NCR,
Yes, which one would it be?
the PR, because the order does matter with the 6 numbers.
Ah, okay. So the order does not matter in this case because check it out. Let's say the machine is random, okay? when you look at one more, huh? When you look at the numbers in the news, they always give them to you in order, but the machine pulls them randomly. So the machine could draw a 17, a 21, a 2, a 1, an 11, we'll call it 11, a 12, and then a 51, right?
But it would matter that you got it in that order.
No, the order doesn't matter. So if you pick a ticket with, put them in order, 1, 11, 12, 17, 21, and 51, this would be a winning ticket. This would be a winning ticket. The order in which they are chosen does not matter. So what does that indicate to us? What type of problem would this be? This would be a combination problem, right? So what we need to do is use the definition. So the probability of winning, okay, is going to be some fraction over the total number of ways that this could occur. So the question is, how many different ways could we choose 6 numbers from the 53? I wish we had like a calculator or something to tell us that answer. Okay. Exactly. So 53, choose 6. This is our number in the denominator, because that number represents all the ways in which we could choose 6 numbers from 53. Does that make sense to you? Okay, so I need that number. So what is it? You guys help me out. You guys figure it out?
22,900,000.
How much?
22,957,480.
480. Wow. 22,957,480. Thank you. And how many ways could you pick that? 1. 1. There's only one ticket that wins, right? Those numbers. So your probability of winning the Florida lottery is that number. Now, actually do that in the calculator. What does it give you?
But the winning ticket has to be in the correct order, but choosing them does not.
No, that's the whole point.
Or does
Yeah,
it matter as long as you get
it doesn't matter as long as you have. So if
If you have the same numbers as someone else, couldn't there be multiple ways to choose?
well, now there could be multiple winners, but there is only one set of 6 numbers that win,
Okay.
right? See the difference?
4 e to the negative, or 4.4 times 10 to the negative
4.4 times 10 to the negative what?
8.
Negative 8. Wow, there you go. Okay. There's scientific notation of that number. So your probability is 1 out of that number. So here we go. We're going to talk about the probability of an event not occurring. Then I'm going to show you a picture and we'll do an example with it, all right? If 2 events are what's known as mutually exclusive, it means they can't happen at the same time, all right? So that means that the event happening with the probability of the event not happening has to add up to 1. So what do I mean by that? Okay. So let's say this, okay? If the probability of rain is equal to 20%, okay? Then what's the probability of no rain?
80%.
80%. Okay, how did you do that so quick? Why is that so intuitive for you guys? How come that's so easy to do?
It's out of 100%.
Yeah, it's out of 100%, right? Because if you add up the probability of rain and the probability of no rain, well, it's going to be 100%. One of the two things is going to happen, right? So the sum of those two things has to be 1. So we take into consideration this fact right here. The probability of not E, is just 1 minus the probability of E. Okay? And many people don't realize that this is an algebra problem. If I were just to add the probability of my event to both sides, probability of my event, notice I would get the probability that it doesn't happen plus the probability that it does, assuming they're mutually exclusive, is going to be 1. And that's what you guys just told me right now, right? The rain example, everyone understands intuitively. The probability of rain is 20%. Well, then probability of no rain is 80%. And that fits that example right there. So why is it important to understand this? Because it really helps us when we're trying to solve problems like this. Okay? You don't need to obviously copy the chart. That's what I did it for you. But let me tell you what you're looking at. It says the circle graph in this figure shows the distribution by age group of 191 million car drivers in the U.S. So I'll write that down. 191 million car drivers in the U.S. Holy cow, that's a lot of car drivers, okay? It says this, if one driver is selected randomly from this population, find the probability that the person is not in the 20 to 29 age group. So what's the probability that they are not in the 20 to 29 age group? Why would it be important to use that formula I just gave you versus not using that formula? Anybody know?
Trying to find out.
Does it save you anything? Is it easier? Is it an easier approach?
It's less confusing.
It's less confusing. It's also less work. Okay, so I want you guys to actually figure it out. Give me a fraction or a decimal. Ready, set, go. Yeah, go ahead.
You do 33 divided by 191.
So this is going to be 1. This is going to equal 1 minus the probability that they are in the age group of 20 to 29. Does everybody make sense in that part? So the probability that they're not is 1 minus that they are. Okay? So that's going to be 1 minus, and then
It's 33 divided by 191.
33 over 191. That represents the probability that they are in that age group, and that's representative of this picture right here from this part, the 33, right?
Yeah.
There's 191 total, 191 million car drivers in the U.S. So that's our total.
Is that from the
That's from the definition.
theoretical probability?
Yeah, yeah. So the probability that they are is 33 out of 191. So the
then
probability
it's
they're not.
191 minus 33.
So then that's just going to be whatever that fraction. You can just plug that fraction right into your calculator. You can just go 1 minus 33 over 191. And that'll work. As long as you keep that in parentheses. I'll show you when this opens up. Okay? So if I go 1 minus the probability that they are in that age group, which is 33 divided by 191.
Like 33 million or no?
Yeah, this is in millions, so we're good. So 0.827. There you go. Boom. 0.827.